All right, good morning, everyone. Thank you for joining us again on RC Design class. Quick announcements. First of all, I finished all the grading, including quizzes on the campus. So please do check on your grades. And if you have any question regarding the grading, email me and we can schedule some talk and help you to go through the grading. All right. And I can see from my experience that we have a pretty good understanding on shear. One critical issue is still relies on the differences between the total web width and the effective web width BW. Okay, as I said again, the effective width for web is the least or smallest narrowest distance across the cross section. All right, so that is the common mistake I see over there. And another announcement is about the CET evaluation. And you probably have received email by now that you're requested to submit the evaluation for this course. I really like to have your input on this course to help me improve. And as I said in the Monday class, as an incentive, if let's say 60% of us that filled the survey, that means 60% response rate, I'll give a 3 points, 3 solid points towards your exam at the end. Okay, when I grade your exams. So I know that 3 points may not sound like a lot, but it is quite a bit, especially for the cases where on the border of deciding which category is B or A. It can pull you up from B to A quickly. So like to you to help me fill it out, so I can also help improve the lecture content. Okay. And last announcement is that we're going to have the lab design next week. Okay. And instead of this weekly lab session, we're going to have a design lab. In the sense is that we're going to talk about how we design a concrete beam in terms of shear and bending moment using the knowledge we learn from this class. But the structures can be a little bit different. It's not a regular section that we went through during the lectures. And we will talk about that on next Monday. And to help you design, we will not have classes next Wednesday or Thursday on the lab design. Basically, I will return the time to you and to help you to conduct the design. And I'll talk into more details about the format and expected outcome from the lab on Monday. All right. But be aware that we will have a lab. And in terms of grading, the lab will be added to your homework and quiz sessions, and it will take as a 25 percentage as indicated from the syllabus as a weight percentage to the total grades. Okay, and again, specific format and it is in terms of group or individuals. Those information I'll talk about in next Monday. All right. Okay, I'd like to make a quick pause here. Any question regarding the 3 announcements I just made? Anything, folks? All right. Okay. Well, if we're all happy with that for now, I want us to come back to talk about the lecture contents. Okay. Again, before we start the main content, you can see from my screen I'm sharing right now, I uploaded a file called transform section for double layer reinforced sections. Okay. So this is a handout where we perform a converted section for ICR to find the ICR basically for a doubly reinforced section. Okay, you can find this on Canvas in the file folder. So quickly to point out, in addition to the tension reinforcement at the bottom, since we will have compressive reinforcement, we need to take that into consideration as well. So we have to take n minus 1 and multiply as prime to get the converted area. But once you convert that, you just have additional concrete to take care of in terms of ICR. So follow the process listed here, you arrive at the correct ICR number. And the other thing is that if this is the positive moment, and you'll be doing this to get ICR, what if this is negative bending moment, right? So if you have a negative bending moment, simply think about it. We just essentially flip the section, all right, and let the top fiber to be in tension, and you can calculate your ICR correspondingly using the same approach. All right. Well, I have uploaded this one to Canvas, so please take a look at it and let me know if you have more questions on this. Okay. All right. That is about it on the transform section for deflection calculation. So today we're going to open up a new topic. All right, new topic. That is development length. Okay, so let me pull my software up again and share my screen. Okay, share my screen. Alrighty. Okay, so today we're going to talk about development length. Okay. All right. I got some message here really quick. Okay. All right. Well, let's come back to the lecture first. Okay. So today we're going to talk about development length. Okay. Development length. All right. So what is the definition of a development length, right? The length, a development length is the length of the bars, the length of bars required. Okay. It is not a recommendation. It is mandated. Okay. Required to be embedded, okay, inside concrete. Okay. This is the length required to be embedded inside the concrete that will develop sufficient stress okay, in the rebar, in the bar. Okay, well that is a mouthful, right? What does it mean? What does it mean, right? And of course, this is by ACI. Okay, this is by ACI 31819. Okay, so what does it mean is that if you think of a cross section of a beam, right? Just say the side view of a concrete beam here, and we already know, for example, if we apply a positive bending moment, and this is in tension, and top is in compression, and we already know the reinforcement need to be embedded, can have a shape like this. Okay, can have a shape like this, right? So if you think of it, the end of the bar is essentially just a hook for anchor, right? So this is the portion for anchorage, where the bar needs to stay in. Okay, and we're pulling the bar out. Essentially, that is from the end of the concrete beam, right? So as we pull it out, and we talked about this during the flexure design, the reinforcement will yield, right? The reinforcement will yield. That means at a particular section, right, moving forward, all the stresses inside the bar are Fy. All the stress inside the bar are Fy. Why is that? Because we need to transfer the stress from concrete to give it to the steel, right? So think of it, when the bar is being pulled out, all the concrete on the sides are rubbing against it, providing a resistance, right? Providing the resistance. And all these resistance build up. Right? So when you add all these resistance up to a certain distance, right? When we add all the resistance up within a certain distance, right? And this distance is just long enough to allow the stress in the rebar to build up to a value of yield stress Fy. Then this LDV is the development length. Okay, that is the definition of development length. So put it in a layman term, it's just a bar that has to stick into the concrete long enough to give you that yield stress in the bar. All right, so that's essentially it. It's just the distance that you have to embed your bar into the concrete to give you that yield strength, Okay, now taking a look at that, right? You may start to wonder, okay, Bob, look, yeah, I understand the length. What about the tail? What about the anchorage portion, right? What about this portion? Let me use a question mark here. So what about this? Does it count? Well, unfortunately, it doesn't. Intuitively, you would think that these anchorage do help, right? They help to get more stress in the bar, right? Think of it. Well, I can intuitively think of it. If a bar is bended and inserted in concrete, even if there's no contact here, I can pull the bar and the end will still hold. You're absolutely right. It will hold Unfortunately, though, this bar is in an angle with the horizontal bar, so it will not provide additional development strength to the bar. So anchor ridge or not will have effect, but that effect is not dominant. That effect is not dominant. So most of the situation in the code, you will still need almost the similar length in development length to build up the stress in the bar. All right. So be very careful, mindful about that. Okay. All right. So that's one caveat. Okay. But now let's take a look at these bars, right? Immediately we realize that the development length, since it's by definition stress need to be built up in a bar, right? So it can be defined or categorized by the stress in the bar. So we'll have equation for the development length for tension, and we will have equation for the development length for compression, and we'll also have development length calculations for hooked bars. That means with anchorage, like shown here. Okay, with anchorage shown here. All right. So straight bars tension, straight bars compression, and hooked bar tension and compression. Those are the categories. All right. So in our lecture, we mainly focus on this. That is tension bar, straight bars. Okay, tension bar, straight bars. All right. Okay. So this is what we're going to talk about. This is what we're going to talk about. Since we're opening a new topic, okay. So I'd like to put some learning objectives here so you know what is the focus, what is the main theme of this chapter, right? So the learning objectives, what do we need to understand from this is first, we need to understand, okay, the definition of development length. And we know that, right? Already, it's quite straightforward. It's just the length, let me say this again. It's just the length that will help you to build up the stress in the bar to reach the yield strength of the bar. All right. So that is the definition. And the second is we need you to know how to calculate this development length. Of course, we'll give you the equation for it and you plug in the right number into it. But knowing why and how. Okay. Knowing how and why. All right. But let's go beyond than just a superficial wording, right? Let's dive into the details about this development length, right? So first of all, the definition of development length. Okay, when I say definition, it's more of the mechanism of development. Okay, so or the mechanism of development. Okay, so another word to explain another word. I hate this most, right, Bob? So what do you mean by the mechanism of development? Is what is in action, right? What is in action at the interface between the concrete and steel, right? So the basic definition of this development length, the basic definition of this development length actually come from the bonding. All right, I want you to keep this word in mind, the bonding, right, between concrete and steel interface, of concrete and steel interface. All right. So if I wear my magnifying glass, okay, I want to zoom in to want to see the exactly interface between the concrete and the rebar, right? What do I see? So I will see concrete first, of course, right? So let me scroll down to show you some pictures. So I see the concrete here. Usually we use this to indicate concrete, means aggregates, means sand, and means space means cement, right? And the bar looks just like this since it is deformed bar. You see, deformed bars. So we have ribs like so. We have ribs like so, and it's symmetric, and so it's both sides, right? And then going out, okay, going out. And just to make it easy to see it, I'm pulling it towards right. Okay, so in case This is confusing. Just say this is force. All right. So I'm pulling it towards right, pulling it towards right. So naturally, as you think of it, right, of course, this is surrounded by concrete. This is surrounded by concrete. Okay. Everywhere you see is concrete outside the bar. Okay. So as I'm pulling away, right, the bar from the concrete, I can see that the concrete trying to resist it. The concrete is trying to resist this. So let's assume at the very left end, right, the very left end, and let me pull up an x-axis. Okay, very left and x-axis, right? So now I can see that there's no stress develop at the very end. Okay, no stress develop at the very end. So as I getting away from left end, first thing I see is the friction. First thing I see is the friction. I use blue color arrows, okay? Nearby this flat region of the bar, right? Is providing that resistance, okay? And I don't see a whole lot of friction on the ribs. Although there are some friction on the ribs, but the ribs are so small, so don't see a whole lot. But I continue to see the friction at the flat regions, all right, at the flat regions, okay? And then apart from that, right, so this is a friction, so let me just write it out. Friction is one component that contribute to this bonding stress, So this is the bonding stress, right? Okay, so as you see it, as you imagine, right, so all this add up, right, add up. And if you care to know it, it follows this hyperbolic equation, okay, follows this hyperbolic equation and reaches to a certain value, So this is friction, okay, this is friction. Okay, now apart from friction, there are what? There are chemical adhesion. Meaning the components of the concrete will react slightly with the surface of steel or rust layer to create a chemical bonding. Okay, and you realize that this chemical bonding also predominantly exists at the flat region of the bar. Okay, at the flat region of the bar. All right, so this also contribute to the bonding stress. Okay, bonding stress. That means my concrete is trying to grab on the rebar, right? When the bar trying to pull away from the concrete, not only I have abrasion or friction, I also have adhesion, right? Something too sticky there, something quite sticky there. All right. So last but not least, right? This is the time where all these ribs start to play a majority or main role here. Okay, now there are two sides of the ribs, right? You notice that I only emphasize the right side because that's where the bearing happens, right? So imagine my bar is going this way, right? My bar is going this way, right? Going this way in horizontal direction, right? So it will try to push the concrete in perpendicular to this rib surface here, right? Push it, the concrete. So the concrete naturally will bear on the surface and provide the last major component of it is what? Is the bearing, okay? Bearing by deformation, okay? Bearing by deformation. Deformation of what? Is it deforming steel? No, I don't think so. Steel is very strong, right? So in this case, it's deformation of concrete, okay? Deformation of concrete. All right, so the friction stays here at the lower figure here, and the adhesion is actually much weaker. So, sorry, I don't like this. The adhesion is much weaker at the lower here. All right, but the bearing is quite big, right? The bearing is quite big. So bearing is predominantly helping the bar to resist the bonding stress, right? To help consist the bonding stress. So you can see that as I'm getting away from the left end, which is zero stress built up in the bar, to the end of the bonding length, and I will develop this stress here. So the stress here in the steel will equal to the yield strength of the steel. Yield strength of the steel. Okay, so now this is very critical now. This is very critical now. The component of the bond, right? So we will say that the bonding stress, right? The bond is contributed, okay, is contributed from the following components, very important components, okay, following components, okay, and these are the following components: friction, chemical adhesion, and bearing, okay, very important, and you need to know that this will show up in the exam, right? Will show that in the exam. But one more thing I want you to pay attention. All this is to prevent what? Prevent slip. Okay. What does slip mean? Meaning we do not allow concrete or bar slip away from concrete. All right. Meaning we do not allow the bar to be running away from concrete. There's always constant contact. There's always constant contact at bar concrete or steel concrete interface. Okay, so this is critical. This is critical. All right. Okay, so now that is the bonding mechanism. That is bonding mechanism. Okay, so we have covered that the three components consist of bonding mechanism. But everything we have talked about before so far have pointed the fingers towards this so-called development length. So-called development length. And we haven't taught you about how we're going to calculate this. So here is the equation for that. Okay, so in the scenario, right? I have a beam or column joints just in case, right? So I have a tension bar, right? Since it is a cantilever, right? Since it's a cantilever, and I'm gonna put my bar on the top since it's cantilever, right? And assume it's a straight bar in, okay? All I need is to try to calculate this L development length is how much bar has to be embedded inside the column, okay? So how do I calculate that? So by ACI, okay, 25.4, 0.2, 0.16, okay, and ACI 25.4, 0.2, 0.3, okay. There's an equation for development length. Okay, so let's take a look at it, right? So this is the basic, okay, basic equation for development length. Okay, when I say basic, that means the longest. Okay, so there are simplified version of it, but today first let's take a look at the basic one, right? So what is this basic equation looks like? Let me show you, okay? So if you look at the ACI code, ACI said, okay, now how much do I need to embed my bar into the concrete to develop the yield stress? That was the question, right? That was the question. So this equation reads like this: 3 over 40 lambda, okay? And this lambda is the lightweight and normal weight concrete coefficient, okay? Lightweight, normal weight concrete coefficient multiplied by the yield strength of the bar Fy divided by a square root of F prime C, which is the concrete compressive stress, okay? So that's the normalized stress factor. And the last factor is a little bit long, okay? So on the top is psi t, okay, psi t, and psi t is a parameter describing where the bar is at, bar location, okay, where is bar location, okay, and then there's another coefficient called psi e, okay, and this is equation, or sorry, factor describe the coating conditions, whether it's epoxy coated or not, and last but not least, there's a bar size coefficient, psi s. Okay, so on the top, all these psi t, psi e, psi s, all these parameters describing the bar conditions, At the bottom here, And this is the confining parameter. Okay, confining parameter consists of CB, which is concrete cover, plus KTR is a coefficient of confinement divided by dB, which is diameter of the bars that need to be developed. Okay, so this whole thing has to be multiplied in front of a dB, which is bar development bar diameter. Okay, and this equation ensures that the bar has to be also embedded more than 12-inch inside the concrete to reach the yield strength. All right, so that is the development length equation. Okay, but be careful. It also states that this equation is only valid when CB plus KTR divided by dB is smaller or equal to 2.5. Now, what does it mean? It means that this confining coefficient, right? This is confinement coefficient, so we call it confinement effect, is limited by a number 2.5. So you can go into it and calculate this, and what if this is bigger than 2.5? So it will be capped at 2.5, meaning if it's bigger than that, you let it equal to be 2.5 to be able to use this equation, All right, okay. So these are the equation. I just spit out all the parameter factors, but let me write them down, okay? Let me write them down. So LDEV, or people call sometimes LD, okay? And this is defined as, use a different color. Anyway, let me continue this. This is defined as development length, okay? Of course. All right, development length. And note that this is in terms of unit inches. Okay, inches. Now, I just want to say here, okay, for some reason, when people do their calculations, right, and when I grade them, I keep saying that for a moment, okay, so this is on a side note, digress, but for a moment, always use unit keep foot or keep feet, right? Keep foot. Okay, for shear, always use keep. Okay, for any other dimensions or sections, right? So geometries, right? Geometries in sections. So geometry for sections, okay? For sections, for bars, everything has to be inches. And this mixed unit thing is not helping. It's not helpful, okay? So try to avoid using pounds and feet, inches, mixing together, and try to avoid like pound, foot, or some odd unit, okay? So these are the common units. Anyway, so let me go back to this. This is the definition of development length, and dB is, we said it, bar diameter, right? Bar diameter. But note that this is the bar being embedded inside the concrete. Okay, and again, this is in terms of inches. All right, and now lambda is a normal weight concrete or not. 1.0 is for normal weight. 0.75 is for lighter weight. Okay, and CB is the concrete cover, right? CB is the concrete cover, okay? And by definition, the concrete cover, I mean, it is a smaller of following, okay? Smaller of following. What are the following? Smaller of these numbers, okay? Smaller of these numbers. So C1, okay? C1 is what? C1 is the corner concrete cover. It is smaller of Cx, which is concrete cover in x direction, and Cy, concrete cover in y direction. Okay, so how do I define Cx and Cy, right? So if I have a end corner of the beam and my bar is somewhere here, okay, so I have two distance. Cx is the edge of the concrete to the horizontal direction of the center of the bar, and then I also have Cy in this direction, Okay, so what if I talking about the bars that in the middle of the section? What if I talk about the bars in the middle of the section? Okay, so Cs for this bar is what? Cs for this bar is the distance between the bars, okay, divided by 2. Cy is right here. Okay, Cy is right here. Okay, And sorry, let me clear this up. Okay, so this is essentially cx divided by 2. Okay, so this is adjacent to bars. All right, now what about C2? C2 is another scenario, okay, another scenario is what? That is by definition half of CC, half of CC. Okay, sorry about this, let me put this is CX. Okay, so what is half of CC? Meaning if I have a bar that in the group, I have bars in the group, okay, more than 2 bars, right? Definitely more than 2 bars. And when I have more than 2 bars, I will have concrete clear cover here, CC. So C2 is half of that. C2 is half of that. Okay, so you can think of it, C1 is for a corner. C1 is for a corner. C2 is for group or bundle of bars. Group of bars. Okay, but that is the definition for CB, the concrete cover. Okay, concrete cover. All right, so these are these parameters. Now let's take a look at the KTR, right? So remember in the confinement effect, there's a parameter KTR here. So what does KTR means? Okay, KTR is actually an equation. Okay, we call it transverse reinforcement factor. Okay, reinforcement factor. Okay, and that is an equation equal to a 40, and just a constant, multiplied by ATR, transverse reinforcement area, divided by S, spacing between the transverse reinforcement, and N, number of bar being developed. Okay, so this is a little bit mouthful. So let me just label here ATR, okay? ATR is what? Is the area of stirrups, basically. Okay, so whenever you see transverse reinforcement, that just means stirrups. Okay, so ATR is the area of stirrups, and S is the spacing of stirrups. Sound familiar, right? It's like shear, right? It's just like shear. Okay, and N is, be careful, okay, this is the number of bars being developed. Okay, being developed. That means how many bars in the parallel plane, right? How many bars in the plane? Okay, now this is still hard to visualize, right? So I can provide you a drawing, hopefully to help you understand what this is looking like, right? So for example, if I have a beam, okay, and this is 3D view, I have a beam, a rectangular section like this, rectangular section like this, and then I have stirrups, right? I have stirrups, okay? So why do I have stirrups? I have longitudinal reinforcement, right? Longitudinal reinforcement. And let's just say I have 4 longitudinal reinforcement need to be developed. I have 4 longitudinal reinforcement need to be developed. So namely, number 1 bar sticking out like that. Let me use different colors so we see better, hopefully. So let me use red, okay? So 1 bar tension sticking like that. Another one sticking like this. Okay, so let's say I have 4, right? Another one goes like this, and another one goes like that. Okay, so these are the 4 bars that will sustain tension and being embedded inside the concrete, Okay, so naturally I need to find out the development lengths for them, right? Development lengths for them, and they're in the same position, so they have the same development lengths. Okay, now I'm talking about KTR, right? I'm talking about KTR. How do I calculate that? So I need to have stirrups. Considering there are 4 bars, and for example, in the seismic zone, 4 bars, that's a good number, but I want to have more stirrups to hold them together, to confine them, right? To hold them together, right, inside the concrete. So let me design a stirrup. It goes like this: a U-shaped stirrups, as you've seen before, has one goes like this. Okay, one goes like this, and another one cross and goes like this. Okay, goes like this. Can I do that? Yes, right, I can do that, right? So these two bars have one stirrups, these two bars have another stirrups. Okay, all right, so this is the end, right? Now, spacing away from the end, right? Spacing away from the end, I say, look, I have a spacing S, okay? Spacing S, and I have another stirrups goes like this, cross these two, right? And I have another stirrups goes like that, cross these two. Okay, so these are the two rows of transverse reinforcement. Okay, now this is a 3D view, right? I have a hard time understanding this above. I don't like it. Fine, right? Let's take a look at the cross-section view. And maybe this is easier, right? Maybe this is easier. So I will take a cross-section, cut it, right? I look from the end, look from the end. So I see now, look, I have, if this is 1, 2, 3, and 4. So number 1 is right here. Number 2 is right here. Number 3 is right here. And number 4 is right here. Okay, and sorry, and naturally my drawing is crooked, right? So forgive me. Let me redraw it so you can see the bars roughly in the center. Okay, and this is exaggerated, but you get the idea. Okay, so this is where the bars at, and I'm gonna put a reinforcement, transverse reinforcement. Okay, stirrups. That is okay. So as I show here, one bar will look like this. Okay, so at the corner goes around it and goes circle around it and sticking out like that. Okay, and then this is actually half a diameter, right? So let me draw it like this. Okay, so that's one stirrups. And I have another stirrups, right? Like I said, it's in the seismic zone, somewhat I'm concerned. So let me just put more confinement to it. And then this is exaggerated, and and then goes up like this. Okay, and this another stirrups. Okay, I can definitely do that, right? I can definitely do that. It's awkward, but I can definitely do that, right? So these are the stirrups. Now, what about ATR, area of stirrups? ATR means if I cut it, right? If I cut it, use a different color. If I cut through it, so make a cut right here, okay? And assume this is number 3. Assume number 3, okay? Assume number 3 stirrups, right? And you know that AV for number 3 is 0.11 inch squared. So how many cut I have, right? I have a 1 cut, 2 cut, 3, 4, 4 legs. So in this case, ATR would equal to 4 legs multiplied by AV, that is 0.11 multiplied by 4, 0.44 inch squared. That's how we calculate ATR, okay? That's how we calculate ATR, okay? I love this function. You may not have it in your notebook, but don't worry, it's just for me. Let me just have more space here, okay? All right, so that is how we calculate ATR, okay? Look at this equation. So S is the spacing between the stirrups. So for example, if I gave 8 inch, that is 8 inch, 9 inch, that is 9 inch. All right, so how about N? N equal to what? 1, 2, 3, 4. 4 bars are being developed. I shouldn't circle this because that is different from the stirrups, right? So there are 4 bars that are being developed, right? These 4, okay? These 4 bars that are being developed. So N equal to 4. All right. So that's how we calculate KTR. That's how we calculate KTR. Okay, so just before we leave this session, think about it, right? So I want you to take a look at the unit here, okay? What is unit for ATR? Inch squared. What is unit for S? For S, right? Inches, right? So you look at the KTR. KTR equal to 40, which is a numerical number, has no unit, multiplied by ATR, which has a unit of inch squared, divided by a spacing S, which have a unit of inch, and multiply N, which has a unit of unitless, right, number. So this has a unit of inch. KTR should have a unit of inch. Okay, and that makes sense because remember we need to calculate CB plus KTR divided by what? Let me see what's going on here. divided by dB diameter, right? So this will be unitless. Okay, and note that this is capped at 2.5. 2.5. All right. A little bit complication, right? A little bit complication, but it's not too bad, right? Not too bad. Now you know how to calculate KTR. Okay. Now we're not done yet. We're not done yet. Remember those coefficient, those factors, psi t, right? Remember those psi t. So let me just go back. So psi t is what we call the bar location factor, right? Bar location factor. Okay. Now what does it mean, the bar location factor? The bar location factor meaning if psi t is 1.3, that means I have more than 12 inch of a concrete, 12 inch of a concrete, okay, placed underneath, placed underneath the bars being developed, the bars being developed, okay, and visualize this thing. That means, you know, my bars being developed is on top. Okay, so that means if I have a bar that being developed right here, one and one here, and say the concrete underneath it is more than 12 inches, then psi t equal to 1.3. Psi t equal to 1.3. So you may say, Bob, this is such a weird definition. Why that? You think of it, it's actually meaning is if I have the bars being developed on top, right, being developed on top, when I pour the concrete, the aggregates turns to drop to the bottom. So there are not much of an aggregates on the top, right? So-called cream, when you do the surface finishing, there are fine cement. So the strength of that is different from the bottom of the concrete when I have a lot of aggregates. And if I have such a layering effect due to the pouring, I have to consider that effect in terms of design. So I have to provide longer development lengths, so to be more conservative. Okay, but anyway, in other cases, psi t equal to 1.0, right? 1.0, so otherwise. Okay, and just in case you forgot what we're doing, right? The bigger psi is, longer development length is, more conservative, okay? More conservative, safer, right? Safer. Okay, all right, so that is the bar location factor. Okay, so next, psi e, right? Psi e is, E represent epoxy, right? So meaning coating factor, So why coating factor, Bob? Because if you think those plasticky epoxy coating, right? Green bars, right? If you drive on a highway, some of the construction not finished, you see some green bars sticking out. You should see that now it's spring. People are still building things, right? And that means you have a reduced bonding, okay? Reduced bonding. So for uncoated, psi E is 1.0, meaning it's just regular length. But for epoxy coated, okay, epoxy coated, because the reduced bonding, smooth surface, weak bonding, right? We have a longer development length, which means 1.5. 1.5, okay, that is quite big, meaning 50% longer, okay? And be careful on one thing, okay? This is with concrete cover. This is with concrete cover bigger than 3 times of bar diameter, or a clear spacing, okay? Clear spacing between bars has to be smaller than 6 diameter, 6 dB. Okay, 6 dB. So these are the criteria it has to satisfy to use this factor, But if it just epoxy coating, however, is not within this category, it will just be a 20%. It will just be a 20% increase. Okay, otherwise. Okay. All right, so that is coating factor psi e. Last but not least, we have a size effect. We have a size factor psi s. Okay, why is that? Because the larger bar that will be developed, okay, larger bar will be developed. Okay, so you have a longer, you need a longer development length. Okay, need longer development length. But for smaller bar need to be developed, you don't need that long, right? You don't need that long. So for number 6 or smaller, okay, turns out that I can reduce my development length by 20%, so 0.8. But if it's 7 or bigger or larger, bigger bars, right? Then you need the full development length. You need the full development length. Okay. All right. So that is my equation for the development length. Equation for the development length. Okay. And you can see that so complicated, so complicated. It has all these factors, right? So let's take a look. All these long equation, all these parameters, everything has to be evaluated. Okay. So it's very complicated. Hence, ACI says, you know what? I understand your pain. If you don't want to do this, if you don't want to do the full calculation for this, I offer an alternative way. Okay. So ACI offer another table, say table 25.4.2.2, and that is a simplified version for this. Simplified version for this. Okay. Which we will talk about it tomorrow. All right. Which we will talk about tomorrow. Okay. All right, I'm gonna pause here. Please, if you have any questions, stay behind or ask me right now, okay? Thank you, or I'll see you tomorrow.